Welcome to Spaceverse, your portal to cosmic adventures. Experts are convinced that the James Webb Space Telescope marks a turning point in space exploration, dividing the field into a before and after era. This is unsurprising given that its groundbreaking discoveries have already revealed discrepancies between our current models and the true nature of the cosmos. Specifically, Webb has identified several structures that, based on our understanding, should not exist in their observed forms. This is particularly true for objects that emerged immediately after the so-called Dark Age, appearing far too large and massive for their early formation period. As a result, scientists are increasingly acknowledging that our conventional theories about the early universe are outdated, and there is still much to uncover before we fully comprehend this complex era. Looking at the vast number of celestial bodies illuminating the night sky, it is almost unimaginable that the universe was once shrouded in complete darkness. Yet, since its birth 13.8 billion years ago, the cosmos has undergone dramatic transformations. During its first 380,000 years, the universe existed as a hot, dense ionized plasma. Over time, however, it cooled enough for protons and electrons to combine, forming neutral hydrogen atoms and setting the stage for the next phase of cosmic evolution. During the period known as the Dark Age, no stars or galaxies existed, leaving the universe without any sources of light. Instead, space was a transparent yet dense expanse filled with hydrogen gas. The return of cosmic illumination occurred roughly 100 million years later, when the first stars and galaxies formed. Their ultraviolet radiation gradually reionized the surrounding gas, stripping electrons from protons and leaving them as free particles. This transformative era, referred to as the cosmic twilight, remains shrouded in mystery. However, observations from the James Webb Space Telescope suggest that it unfolded quite differently than scientists previously believed. Designed specifically for infrared astronomy, Webb's primary mission is to peer into the most distant, and therefore oldest, regions of the universe, offering a direct look at the events that followed the Dark Age. The findings so far have been remarkable. By 2023, Webb had already identified 6 early galaxies that defy conventional astrophysical understanding. These galaxies existed just 500 to 700 million years after the Big Bang, yet they had already grown as massive as the Milky Way, a phenomenon that challenges existing models of cosmic evolution. Each of these 6 early galaxies contains at least 10 billion solar masses of stars, with one reaching over 100 billion, an astonishing amount for such a young cosmic age. To account for their existence, either the density of matter in the early universe must have been 2 to 5 times greater than what the standard cosmological model predicts, or these galaxies must have grown in a way completely unknown to us. Given this, it's no surprise that scientists have dubbed these enigmatic structures universe breakers. Yet, this was only the beginning of a series of baffling discoveries made by the James Webb Space Telescope, each challenging our understanding of cosmic evolution. One particularly striking case is JWST 14-0, a galaxy that emerged just 290 million years after the Big Bang. Even at this early stage, it appears far too large and packed with stars for what was previously thought possible. The mystery remains, how could a galaxy accumulate several hundred million solar masses of stars in less than 300 million years? This finding forces a major reconsideration of previous assumptions, as scientists once believed that only tiny, low-mass galaxies existed at that time, until Webb unveiled the true nature of the young universe. Theoretically, this all aligns with our current models. After all, according to standard cosmology, there simply shouldn't have been enough ordinary matter so soon after the Big Bang to form such a vast number of stars in such a short period. And yet these massive galaxies exist, just like the recently discovered red monsters, which once again challenge our understanding of early galaxy formation. Could it be that the standard model of cosmology is flawed? With the universe continuously revealing unexpected structures that contradict established theories, this question is becoming increasingly difficult to ignore. If so many findings deviate from predictions, is it possible that the model itself is fundamentally incorrect? To investigate this, a research team led by Mangan Shah from the University of Geneva has undertaken a systematic search for more of these early outlier galaxies. By analyzing data from Webb's near-infrared camera, the team identified 36 additional massive, dust-shrouded galaxies that existed roughly a billion years after the Big Bang. Thanks to Webb's high-resolution spectroscopy, they were able to see through the dense cosmic dust that had previously rendered these galaxies invisible in the optical spectrum. Among the newly discovered galaxies, 3 stood out due to their immense size and deep red color. These red monsters are nearly as massive as the Milky Way and appear to be exceptionally active in star formation, adding yet another layer of mystery to our evolving picture of the early universe. In numerical terms, this translates to staggering star formation rates of 795 to 1,300 solar masses per year. However, rather than solving the puzzle, this only deepens the mystery. For these red monsters to produce so many stars in such a short time frame, they must be converting gas into stars at an exceptionally high rate, far beyond what is typically observed. According to researchers, their star-forming efficiency is 2 to 3 times greater than what is considered the maximum for younger galaxies. Normally, galaxies can only utilize about 20% of their available gas for star formation. Yet the red monsters appear to have bypassed the usual processes that limit this efficiency, allowing them to form stars at an unprecedented pace. What does this mean in a broader context? Interestingly, the findings offer some reassurance for the standard cosmological model. They suggest that an extraordinarily high matter density in the early universe is not required to explain the existence of these massive galaxies. However, the discovery also indicates that star formation and galaxy evolution may have followed a very different path in the universe's early days compared to later epochs. Shia and her team argue that their findings strongly suggest the early universe was 2 to 3 times more efficient at galaxy formation than previously believed. However, the exact mechanism behind this remains a mystery. What is clear, though, is that the discovery of the red monsters signals a new chapter in our understanding of the early cosmos, one that not only challenges our view of the distant past, but also raises questions about the present. Webb has also revealed another major puzzle. The universe appears to be expanding too fast. It is well established that since the Big Bang, the universe has been expanding and at an accelerating rate. To account for this acceleration, scientists have proposed the existence of dark energy, a force believed to counteract gravity. Yet beyond its theoretical role, very little is actually known about it. One of the most debated aspects of this expansion is the exact rate at which it is occurring. This is where the Hubble constant comes into play, a fundamental cosmological value that describes the speed of expansion. However, there is a major issue. The standard cosmological model predicts a Hubble constant of roughly 67 km/s per megaparsec, meaning that for every 3.26 million light-years, galaxies should be moving apart at an additional 67 kilometers per second. In theory, this should be the case. However, real-world observations, based on data from supernovae, gravitational lensing, and variable stars, suggest a higher value of 73 km/s per megaparsec. To put it into perspective, this discrepancy translates to an astonishing 20,000 kilometers per hour per megaparsec. But what could be causing such a significant mismatch? Could it simply be due to measurement errors? That's precisely what Adam Rees and his team at Johns Hopkins University aim to investigate when they used the James Webb Space Telescope to reanalyze data previously gathered by Hubble. However, their findings only reinforce the mystery. After evaluating the largest Webb dataset to date, they arrived at a Hubble constant of 72.6 km/s per megaparsec, once again contradicting theoretical predictions. According to Rees, all signs indicate that our current understanding of the universe is incomplete. One possibility is that an unknown factor provided an unexpected acceleration to the early universe shortly after the Big Bang. Alternatively, dark energy may possess properties we have yet to uncover, or exotic particles could exist that help explain the discrepancy. And that's it. The universe keeps rewriting the rules, and with every discovery, new mysteries emerge. Stay curious and subscribe to Spaceverse for more deep dives into the cosmos. See you on the next journey.